Um, I'm Salman. Over here is Chiprian. We work both in Cisco systems and basically I've been with Cisco for almost 9 years, working with the high-speed customers and large enterprise customers. And for last 2 years or so, I'm working quite a bit with IPv6 deployments and designs. Chiprian over here also, we work in pretty much the same team, working with IPv6 deployments and designs and whatnot, anything related to IPv6 pretty much these days. So the idea is that in today's presentation, we just kind of share with you, bring some of the what's going on out there, what are the main deployments, what are the different ways of doing things, what are some of the things to look out for. By the way, how many of you over here are currently testing or doing something with IPv6? Okay, quite a bit. So these are like you have done anybody has done any kind of deployment, or it's more in the lab environment? Okay, good. So is this something related to from any broadband ISP or internet too? Sure, that's very good. So so maybe for some of you, some information will be redundant. So just kind of bear with us, and for some of you, these things will be more informative. Most of you have these slides, or are these slides already available, right? Okay, I'm not sure. So we have like quite a bit of slides over here, and we have 90 minutes to cover them. So me and Chip, we might gonna skip some slides, but because they are more for your reference later on. And after the presentation, if you still have any questions, we'll be around here, so you can come and ask questions. And so first thing, a quick update that what is IPv6 address looks like, right? So it's like 128 bits. So the first 3 bits tells me that this is a global unicast routable address by 001, which is 2, right? Followed by 45 bits. So the first 48 bits is the provider part, followed by the subnet ID, and then the fixed interface ID, which is 64 bits. Some of the basic things, I'm not going to go into details, because our main goal is, to get you into the deployment section and talk about more the deployments. We have basically put together 3 case studies. One is for native IPv6 deployment, then one is for 6PE, and then one for deployment in the broadband area. What people are doing in the broadband area, because one of the things what we are working on right now is the activity more related to IPv6 is in not in US, it's more in Asia Pacific region and RIPE NCC, like in some European countries. For instance, in Switzerland and Netherlands, in Germany, in France, these are all broadband service providers who are providing, using IPv6 to provide broadband for their broadband customers. Also, the biggest customers, biggest places which IPv6 is being deployed is Japan, and the customer who's doing it, the commercial deployment, it's also in broadband. And so we'll also talk about one of the case studies, that how they are doing it. Okay. So the address allocation policy is pretty much, they have this hierarchy in IPv6. So the INA is on the top with the /16. Then we have all of these different registries. So INA gives like /23, and from there, the different registries, they assign /32s to the ISPs. The ISPs assign /48 to the customers, to the sites. So if you remember in the previous slides, the /48 to /64, you have these 16 bits over there, right? So depending on, the ISP doesn't have to give /48 to their customers. This is where basically they would be making their revenues also depending on how many bits they give to the customers, right? They could give a /64 or /56 or /50 depending on the number of bits, because more bits a site would have, they could have, you know, more room to play with the bits and do more things. So this is how it's kind of summarized. So in this particular example, we have 2001, which is a global unicast routable address, a /23, which is a registry. Registry assigns a /32 to an ISP. ISP assigns a /48, and then from /48 to /64, those 16 bits are basically, you know, if I'm a site, if I get a /48, I have these 16 bits, right? If I have 2 to the power 16, I could have this many subnets, for instance. So in this one, you know, keeping that hierarchy in mind, so we have the IPv6 internet /16. Then we have the, in this example, 2 different ISPs, and of course these are from the same registry. So we have /32s over here, and this ISP is assigned /48. So while advertising the routes, you know, these customers only announce a default route to the upstream ISP, and the ISP is announce the /32 to the IPv6 internet. One thing, you know, we haven't covered in this. You'll notice that, you know, some of you might think about what happens when the customers are dual home, right? What happens with the multi-homing, right? So the multi-homing right now, it's not anything different what we do in IPv4 when we leak the more specific. This is some a major, like a known problem in the working group, and there are 8 different drafts which are being worked on to resolve this particular problem. That what will happen, keeping this hierarchy in mind, when you have multi-home environment and you're going to 2 different ISPs, how you're going to do it. So that's something, you know, if you go to the IPv6 working group, you'll see like different drafts which are being worked on right now, and there's nothing like solid solution that you just do this, you know. So there are several different options, and for instance, like right now, people, what they're doing, they just leak the more specific, you know, when they do the multi-homing. This is a interesting slide, like what I was saying before, that more activities in the Asia Pacific region and the RIPE NCC, which is Europe and all the Asia Pacific countries, and the NCC errand is like the right now it's kind of not that much activity, but now it's picking up quite a bit. One of the reasons was that the Department of Defense announced last year that they want to go to IPv6 by 2007, you know, so that kind of accelerated the whole thing. And I'm not sure that how many of you are aware of the applications, but the things that I was in Santa Barbara when there was the IPv6 forum conference, and that's where they made the announcement. So the applications they were talking about is like pretty advanced and things what they want to do, you know. So right now we cannot go into all of those details, but if you just look up, you know, on the internet, you'll find out some details on that. As far as the routing is concerned, nothing has changed. You know, you're still doing the longest prefix matching. You know, nothing has changed. All the routing protocols which are there for IPv4, you have support for IPv6 also. There are some minor changes which are done in the protocols, but as far as the protocol, the way it behaves is pretty much same in all the protocols except OSPF, right? OSPF has some other more than minor changes the way it behaves, you know, because now you have more certain number of more LSAs introduced, and some of them are renamed, some of them are merged, you know, so the functionality is a little bit different than only just doing the NLRI or doing some longest prefixes. Support for longest prefixes is more than that. Okay, so all the as far as you get, most of you know that RIP-NG is the for IPv6 based on RIP version 2, and then we have EIGRP for IPv6, OSPF version 3, and integrated ISIS. So as I said, for OSPF, you have quite a bit of changes, which are the way the protocol behaves. It's a little bit different now. But when we first started to support IPv6, the first thing, of course, was RIP NG because it was easier to implement. But after that was ISIS, which most of the vendors started to support because the way ISIS works and the whole TLV concept, So if you remember that initially when the ISIS came, it used to have 5 TLVs, right? And then when we added IPv4, we added 5 more TLVs. But when we added IPv6, we added 2 more TLVs, and it was pretty much ready to support IPv6. That was one of the reasons that when they started to support IPv6 for link state protocols, it was ISIS before OSPF, because OSPF needed more work to be done. You could have a basically concept of ship in the night for OSPF, where you have OSPF version 2 and OSPF version 3 are running. At that time, you'll have basically 2 different SPFs running. So once you're doing that, you have to keep just saying this, that you can do it. It's just the easy thing to say, but once you really deploy that, you have to keep a lot of things in mind. For instance, you'll have to make sure when you make these routers, a dual stack router supporting OSPF version 2 and version 3, you got to make sure that you have enough memory, enough processing power, because now you'll have this router basically running 2 different SPFs, right? You'll have 2 different routing tables, so the packets will coming for v4. You'll go look into the OSPF version 2 forwarding table, and then for version 3 it'll be different, right? So it'll be double the the processing power and everything. So you have to, once you we have customers right now who are doing this, but you have to make sure that you're meeting all the guidelines, right? So there's no easy way like to just put 10 pounds of sugar in a 5-pound bag. So you have to basically follow all the guidelines. The other thing is that ISIS, as you know, that is being supported right now, but the other concept is ISIS multi-topology, which is also being supported right now. So you could have 2 different topologies, 2 different SPFs, because right now with ISIS, the way it works, you can only have a single topology for both V4 and V6. But with multi-topology, you could have separate topologies, which is also supported right now. Then you have BGP, right? So BGP was easy, right, for V6. So they're using multi-protocol BGP. Now they have another address family, AFI2, which is for IPv6. Of course, all the sub-address families are same in all the address families. That was like a very quick update, what's going on around the world, what are the things, some related to IPv6. So SP deployments, right, activities. Basically, you have several market segments, the internet exchanges, the transit carriers, the regional SPs, the wireless, mobile operators, and each of them, they could be doing things a little bit differently than others. But as far as the main, I'm kind of right there, so if I fall. So basically, but mainly, for IPv6, there's no, cookie cutter approach, or there's no, deadline or anything that, this has to happen by this date and all around the world because we are running out of something, or there's some deadline or Y2K or something, nothing like that. So it's all going to depend on the requirements coming from the customers, right? And what they want to do, what they're asking for, if all this investment or whatever we are doing making sense or not. So depending on different countries, regions, even in countries, different cities, all that sort of stuff. Like we were working with one customer in Malaysia, in Kuala Lumpur, they are doing something, with wireless, IPv6, they have these hotspots, they want to do this thing in KL, in Kuala Lumpur. So it all depends, where you are, what are the requirements. For instance, in Japan, basically they're deploying IPv6. That's one of the biggest deployments in the world, and they're focusing on all the broadband customers, right? And so keep in mind that like you're kind of shifting from this dial-up environment to a broadband environment, right, where you have always on connectivity, and there's no more you go there, you dial up, you get the address, and once you're done you release it, someone else uses it. Now it's like broadband environment, things are pretty much up all the time, and the address is going to be needed all the time, right? And then another big application for IPv6, which is being evaluated, and also a lot of things are going on in that part of the world, is in the mobile, right? So if you see where we live right now in this part of the world, or even in the Europe, you get pretty much the landlines and all these things are no problem. But if you pick up like the 4 or 5 big countries in the world, right? Indonesia, India, China, Pakistan, Bangladesh, these 5 countries, we have more than half of the world's population. And even to this day, in majority of the cases, if you go, you cannot get a landline very easily, right? It takes time. At that part of the world, there's there are jokes that if I apply to get a landline, maybe my kids will get it. So it takes quite a bit. Yeah. And but at the same time, even I'm originally from Pakistan, and when I go there to my village, somewhere, a person they wouldn't have a landline or anything, but if they go to a town center or somewhere, they can still get a mobile phone, right? And they can get connected, right? They can make phone calls all over the world. So the applications people are thinking, and in that part of the world, things are being tested, that let's say on this mobile phone, you have an IP stack, right? And if you have an IP stack on this mobile phone or PDA or whatever it is, right? Now you can get this guy connected on the internet as well, right? So this thing is basically connects to, if you know about the 3G, right? The 3G gets you 2 megabits rates, right? And 3GPP, which is the body for all the standards, they have chosen IPv6 as the de facto stack on all the devices which are going to be built in future, like which are billions, right? So basically, that if you have this PDA or mobile phone or whatever it is, with the IPv6 stack, the opportunities are pretty much are pretty big, because that this guy can get connected on the internet. At the same time, if you have some local provider who's providing some kind of stream of the interest of those people, right? If it's like cricket highlights or anything, Indian movies or whatever, the songs or whatever the things people like, they could put a local server, and people most of the time they could watch on this this PDA or whatever the small device they have. They could do quite a bit. And also, when we work in that part of the world, things doesn't have to be big, like over here. Things, people, if you even have smaller things, people are happy with it. So those are some of the things people are evaluating right now as far as the V6 and this whole market is concerned. Sure, right now we can do it, but we'll have to do NATPP, right? Which is the same concept like NAT, private to global addresses. NATPP is basically between IPv4 and V6. I'll just maybe skip some slides, and we'll go into details later on. As far as the IPv6 deployment scenarios are concerned, for the core of the network, you could have a native, right? So when I say native, it means that you're not going to have any IPv4, you're going to have a dual stack environment, right? So you have all of these devices which are dual stack, they're supporting IPv4 and V6, right? So you have 2 different forwarding tables. Remember the things I talked about, all the limitations, all the guidelines you have to meet, the processing power, all the the memory and have all the, gotta have hardware forwarding and all those things you have to keep in mind. Or you could have in the core, you could have, maybe you're running MPLS, right? So as you know that you have two camps over here. So if you're doing MPLS, you could do still 6PE, and you can deploy IPv6 in a pretty nice way. Which, in fact, for this particular case, we have a case study, and we'll go in details about how you can do that. As far as the access is concerned towards the customers, you could either do tunneling between your access points and the customers, or you could also do a native. When I say native, again, these 2 points are dual stack, and you're doing some kind of, RIP NG or something, routing protocol for V6 and exchanging routes. So all of these things are basically right now being done, on different, like some people are doing one thing, the other people are doing something, the other thing. And one thing to keep in mind, that DECnet was not very popular, at any time as compared to IPv4, but we still find DECnet, right, in the customer networks. So IPv4 is like big, right? It's pretty much deployed everywhere. So it's going to take time, to get towards IPv6s, and it's all going to depend on what people are asking for, and the applications comes along, and the requirements come along. As far as the deployment is concerned, for enterprise and ISPs, things, what they have to look for is pretty much same, As far as they could take, it could vary in a little bit of cases, but as far as the major components are pretty much same. That they have to make sure that, they have to do all the addressing part, and then they have to choose the routing protocol, right? And then they have to make sure that the DNS environment is ready for that, right? So DNS is, we'll just look into that really quick, but basically you have the A records, and for V6 you have the quad A records, right? So DNS is ready for that, to support that. And also the transport is also available, okay? So V4, V6 transport is also there. And about the management, how these IPv6 devices are going to be managed right now, to this day, right now we do all the management, the transport is V4, right? So how are you going to do it? Are you going to, these things to keep in mind. What would be the security rules, right? One thing about, choosing the routing protocol, that you have to kind of keep things in mind, and from the point of view that let's say you have a OSPF version 2 running in the network right now from point A to point B, right? And you plan to deploy OSPF version 3. So you have to kind of make sure that you know all the details about the first implementation. What I mean that you have to make sure that the person who deployed it, like let's say in the past, they played with the matrix, right? So from point A to point B, let's say you have a path A, the preferred path, but it's not the path which is being taken because they played with the matrix, right? So now you deploy OSPF version 3. So now that will be taking the most optimal path. So let's say you run into some kind of issues, right? Some problems, and when you're troubleshooting that, it'll be a pretty big problem because the end user are going to say that with V4 things are working okay, but V6 not working, things are not working okay, because at the end of the day you'll have to kind of make sure that you know all the details while deploying this thing. As far as the transition and integration is concerned of IPv6, most of the things are, you have these, in customer networks, lots of them, you have these islands of IPv6 right now. And these islands are being connected by doing certain things. Like I said in the previous slide, you could do tunneling, you could do MPLS 6PE, those sort of things, right? There are certain things which you could do. There's no expectation right now that people would just rip off their IPv4 networks and put in IPv6 in there, right? So you have to just kind of get the integration going, in a little, even if, you're not going into like a big deployment or something, you could still start, have these little islands of V6 and get them connected and start playing with it or something to get used to and get an early start. That's right. Right. The PE routers will be dual stack, right? And for this particular 6PE, we have a whole case study, so we'll go into more details at how that whole process is being done. I'm trying to, that'll be a really interesting part for a lot of you folks over here. So as far as the integration, the transition and coexistence is concerned, you have, you'll have dual stack, you have tunneling, and you have translation, right? So dual stack, I talked about what's the dual stack, right? As soon as you have, by default router is is forwarding IPv4 packets. Well, then I shouldn't say that, because for Cisco, we were doing IP and Apple Talk and all this stuff. There was like 3-4 stacks. So this is just the addition, but why they use dual stack? That usually routers do IPv4, so they basically, once they start doing IPv6, they're dual stack, right? Or you could do tunneling, right? And this point of when you do tunneling, only the tunnel endpoints will be dual stack, right? Then everything in between is going to be whatever it is. And then you'll have some translation going in certain part of your network, because what's going to happen, okay, so in fact I have some slides on this particular thing, but as far as what you do in tunneling is, if let's say you have IP network and you want to tunnel Apple Talk, right? So the two tunnel endpoints, they'll take Apple Talk packets on one tunnel endpoint, right, where the tunnel starts, encapsulate them into IPv4, transport it over the IPv4 network. It lands on the other side, that tunnel endpoint, that decapsulates, right? Puts and sends the the Apple Talk to the Apple Talk IP, right? So that's the main process. So dual stack approach, just a little bit, one more slide on this, that you have a frame protocol ID for IPv6, right? So which is 0x86db, right? So basically, depending on, this is the preferred approach, right? So depending, you can make your devices dual stack, and depending on the applications, when they start to come along, they can choose whatever, IPv4 or V6, they can do whatever needs to be done as long as it's there, because there's only going to be API which needs to be written, and they can recognize this frame protocol ID. Okay. This is some, reference slides for DNS, but as far as, the DNS part is concerned, that this is one of the good slides, that in a record, what you do, right? You do from a domain name to IP address, and from quad A records, you do basically from your name to IPv6 address mapping. And then you have the PKR records, the reverse of that, right? So this is basically a part that you have to kind of make sure that you're supporting that. One thing to keep things in mind, that for when you're deploying DNS, right? You have to make sure that it's not only you have to make sure that the DNS server is ready to support like A and the quad A records, right? And at the same time, the transport is also available. The root servers, where it's sitting, is not like your IPv4 environment and root server sitting at the V6 environment. It's not going to work, right? Or if you're in the V4 environment and the root server sitting at the V6 environment, it's not going to work. So the transport has to be supported as well with the DNS, like A records and quad A records, whatever the case is. So in this particular example, if I want to go to a.com, right? So I send a request. You know how that basically works. These are some basically reference slides. I could also do an asterisk, right? So if I send that request, I'm going to get v4 and v6 addresses, and based on the application, it will go get connected to wherever it likes to. This is what I was talking about, that let's say you have an IPv6 environment and you send a request and it goes to the root name server, but that's the IPv4. It's not going to work. Okay. And on the other case, okay, I wasn't aware of this animation. Sorry about that. So in this particular case, if you have an IPv4 environment, you send a request to a local name server, send it to the root name server. For this particular example, you go to me.ip6.acme.com, and it goes to this root name server.com, and then it comes back and says, okay, by the way, the delegation for this is this server over here. It comes back over here to acme.com. It says, okay, the delegation for this is sitting at this root server, right? And at the end, when it comes over here, it's only supposed IPv6, right? So it's not going to work for you. So the transport has to be available also. So these are some of the things to just kind of keep in mind when you're deploying the DNS for IPv6. The dual stack infrastructure we talked about, as long as you're meeting the requirements, you have enough memory, enough processing power, all of these things are being taken care of, you should be pretty much fine. But there's no way in service provider environment that without meeting the guidelines, you're going to jeopardize your current IPv4 network, which certainly we don't want to do. I've been with Cisco for almost 9 years, and I started my work in the TAC, and I was there for 5 years and with the pager all the time. So but now things are pretty good, because it took time for people to stabilize those networks. So we certainly don't want to tell people to take out v4 and put the OSPF version 3, right? So but it's going to be more of a integration in a way that start from a little bit of sites, and then you analyze and you expand from there based on the needs. This is some basically very some basic slides that what do you do on the router to make it a dual stack. These are some tunneling. There are different kind of tunneling mechanisms which are available to tunnel IPv6 packets into IPv4 over IPv4 environment. There are manually configured tunnels, semi-automated, and automatic. This almost sounds like different kind of guns, and I'm just at a wrong place, to talk about these things. In fact, I come from Pakistan, and we just grow up with these things, and it just happens to be this way, manual, semi-automatic, automatic. So, manually configured tunnels. It took you guys a while to understand the joke, huh? Okay. We have this manually configured tunnels, right? So you have basically nailed tunnels, right? Pretty easy, source destination on both sides, and you tunnel the traffic, right? Then you have GRE tunnel, which is exactly the same, nailed tunnels. But remember, these nailed tunnels, if you kind of expand, the more sites you have, it's not going to be scalable, right? Why would you want to do one or the other, manual or GRE? They're pretty much same, nailed tunnels, but some of the cases when you do GRE, like in certain cases, let's say you have these islands of ISIS, right? And the ISIS also sends these layer 2 messages, right? So GRE is the only tunneling mechanism which can also carry with the layer 3 information, the layer 2 messages, right? So if you have these islands of ISIS and you're trying to do manual configured tunnels, it's not going to work for you, because the manual configured tunnels is not going to pass any of the layer 2 information. Okay? So in that case, you'll end up doing GRE instead. Then you have this concept of semi-automated tunnel broker concept, which is, I think I have a slide. I have slides on that. I'll show you in a picture. Then you have automatic tunneling mechanisms. The two of them which are pretty popular is 624 and isotap. 624 is automatic because you'll see in the configuration that you do not configure any destination. The destination is found on the fly. So only configure a source address and the destination. So it's basically a point to multi-point tunnel. So it's much more scalable. And then you have isotap. Isotap is again an automatic tunneling mechanism. It's more used in a enterprise environment. Okay. So let's say I work for Cisco, right? So Cisco IT provides isotap, tunneling. I could do it. My Cisco environment is all IPv4. Let's say if I have a Windows XP machine and running IPv6, I want to get connected to the IPv6 work. So what I do, I just basically make sure that I configure my part, the isotap tunnel point on my part, and the Cisco IT has put a isotap router, which is just what? A dual stack router. Okay? So I can make a tunnel over IPv4 infrastructure from my point to the isotap router. And that isotap router is basically a gateway. It can get me connected to anywhere on the IPv6 internet. Okay? So that's the idea. So if somebody asks about the tunneling, so this is a good example, and you can just keep it, just kind of see. So only the tunnel endpoints are dual stack in this case. So so when the packet comes in, basically all you're doing is just encapsulating into IPv4 header. It could be done between the routers or the hosts. Since this is all operational, people who work with the networks, I have just a quick question. That let's say if I have a simple tunnel, point-to-point tunnel, and this tunnel is not coming up. I've checked the configuration, everything is okay, right? And I'm tunneling IPv6 over IPv4, right? Network. What would be the case? Things, let's say, looks okay. One of the, in fact, there was one time I just troubleshooted this thing. Remember that in the slide I said that tunneling is the IP protocol type when you tunnel the packets, IPv6 packet into v4 is 4P1, right? So this is, you could have a point-to-point tunnel, which is a virtual tunnel. There was a router in between somewhere, which was, what it was doing, it was blocking protocol type 41, right? So everything was okay, but this tunnel wasn't coming up, and then it took us a while to just get to that thing that router in the middle, it was blocking that protocol 41. This is an example of manual tunnel configuration right here. Pretty simple. Tunnel source destination, tunnel type, IPv6 IP. Nothing else. Nailed tunnels on both sides. GRE exactly the same. Only I told you when would be that. Some of the cases when you would want to use GRE and not the manual configured tunnels. They're both same. If the network is big or something, or you want to do tunneling, it's not really scalable. This is the tunnel broker concept. These are some of the services which are available right now on the internet. So a person, let's say if I'm connected from my ISP, which is on IPv4, and I have a Windows XP machine at home, and I want to get connected on the IPv6, go get connected to the IPv6 internet, I can basically go to this website, whoever is providing this tunnel broker services, and I can fill out all this information, and that tunnel broker server basically push all that information to a dual stack router, and the tunnel is formed between the dual stack router and my machine at home, right, over the IPv4 internet. And that dual stack router has a way to get to the IPv6 internet, right? So these are some of the services which are available right now. In fact, right now if you go to 6bone.net, these services are available for free. So if you're at home, all IPv4, if you have a Windows XP machine or something, a dual stack machine, you can get connected on the IPv6 internet. This is the automatic tunneling, the 64. 64 tunneling, for this particular type of tunneling, you have a reserved address space which starts with 2002. So the first 16 bits are always going to be 2002. By the way, this particular tunneling type is, is for people who never got a chance, to get an IPv6 address, a global unicast routable address, right? They could just use 2002 and then put IPv4, public IPv4 address, and the following 32 bits, and they can make the address look like a global unicast routable address because it starts with 2, right? So, but it's only used for the environment, for large environment. It could be enterprise environment as well, where people want to get their sites connected on IPv4, and they want to taste they want to test the whole environment and get used to it. But obviously, they want to. The main thing is everybody should try to go to 2001 address range, not 2002, which is only fixed for 64 tunneling mechanism. I'm just seeing how much is it already. 45 minutes, huh? Okay, so there's too much information here. A lot of it, I'm going to skip the 64 tunneling type in the configuration. 64 relay services is basically just really quick to tell you that people what they're doing, that the 624 connects the 2002 sites together. But what if a 2002 site want to go to a 2001 or internet, IPv6 internet or somewhere else? For that, you'll have to have a 624 relay services. A 624 relay router, again, is a dual stack router, which is a gateway between a 2002 and the rest of the world. Okay. Then you have NAT-PT, which is again what it's doing in brief. What you do in NAT right now, 10.0 addresses to the global addresses. Same thing is happening between V6 and V4. I'm gonna again animation. Sorry about that. I'm going to skip some of this because we really want to get you, to some deployment parts. And okay, so let's, what we Chip will cover the deployment part. So what the idea was that we both do 45 minutes, but and I'll cover that part in 45 minutes, so which wasn't possible. So since this is I think this is the last section, right? Last session. So I would really encourage that even if it's going over 90 minutes, just kind of stick around, because this part is going to interest you even more. Okay.
A lot. I think it's really good, but hopefully we're gonna get excited about it. Just a few points I wanted to start with. Making some notes while Salman was presenting. Very little of the information that's actually available in the slides. I definitely encourage you to go through them. It's really interesting. So first of all, as an argument, why IPv6? Deploying IPv6. Addressing still remains, the larger addressing space still remains the main driver. However, what we noticed is that in the process of trying to come up with business cases to justify the expense of going to IPv6, which in some parts of the world is encouraged by legislation or tax breaks, so on and so forth, people try to find new ways to deploy services. So you build an IPv4 network. Now you try to squeeze the last drop out of it. Try to put on top of it all the services that are possible. VPNs, multicast, all kind of SLA supporting services and so on. But sometimes the way you started that big network and that big investment might not be the best way that you could have done it, and you learn that along the way. IPv6 sometimes can offer you the second opportunity, the second chance to squeeze some more out of your network, and this time maybe do it better. So besides looking at the large addressing space which you need, you might see IPv6 as an opportunity to do things better. The other observation that I wanted to make is, obviously when you're going to start talking about deploying IPv6, you're going to have to balance investment versus return. And oftentimes this is going to be driven by your customer needs. The whole idea is, if you have few customers and you don't want to put too much money up front, then it might be worth it to try to do as little as possible to service those few customers. However, if you sort of look on the long run, with the current state of IPv6 and with the current support of IPv6 by the network engineer, it might be worth taking a second thought and considering going for a full-scale, long-term deployment. And I'm saying this because the question of tunneling came up, and everybody's interested in tunneling, and everybody in IPv6 world was interested in tunneling and developed tunneling mechanisms in order to help people or encourage people to implement IPv6 with as little investment as possible. So we are getting to a point where it might be worth it to consider going beyond tunneling, going to dual stack 16. Okay, so that will be my first speech introduction. So we're gonna discuss 3 case scenarios. One would be a dual stack. Dual stack refers to the fact that we are trying to look at both IPv4 and IPv6 in coexistence. Obviously, when you're gonna deploy IPv6, besides all the discussion about money and how much it's going to cost and how much you're gonna get back, you have to make sure, like Salman was mentioning, you have to make sure that your impact on IPv4 is not significant. That's my request. So that's why along the way we will talk about V4 and V6 in parallel. Now, it's very tempting to perceive or to take your approach on developing the deploying IPv6 in the same way you deployed IPv4. Makes sense? You're used with it, you have the same concept in mind, you're familiar with. Whoever is going to do it is already trained into it, right? Most times that works, but sometimes things are a little bit different. So talking about dual stack, that means that in your network you are willing to turn on IPv6 along, side by side with IPv4. So on your interfaces you have IPv6 enabled on top of or next to IPv4. Now, obviously, when you do that, you better be sure of the consequences. You better be sure of the memory size that you have in those routers, that you're taking the routing information for IPv6. Make sure that you have the router has the ability to process, to build the routing tables, run the SPS, and so on and so forth. Now, let's assume this case in which we are willing to do this. And what we do is we have 2 campuses. One in San Jose and one in RTP, might remind your company. Both these campuses are connected to a next generation internet service provider that in turn can take you out to an inter-exchange. So this company applies for prefixes. So they want to get their own prefixes. The prefixes assigned are /48, allocated by the service provider. As Salman pointed out, we're talking only about one service provider. Multi-homing, we just don't want to get dirty. So we have 2 campuses. When we look at the San Jose side, we distribute our prefix along the router. The San Jose side has one link to the service provider, the other link to the RTP office. Now, someone was talking about the prefixes that start with 2, which are the global unicast addresses that are currently being assigned. This is a little bit of an older slide that has a 3FFE address that is, for 6 going, but still works. Concepts are the same. A slight difference in how the address starts. And now, as you can see, we decided to choose 2 prefixes. The 2 prefixes are highlighted down at the bottom. /48 is for entire company, but we decided to assign a /56 on one campus and a /56 on the other campus. Then we go ahead and start configuring each campus with the addressing scheme that we first planned, we thought about. As you can see, the 3 routers, they have the links configured with /64s, and then also the links that provide access to users also configured with /64s, all cut out of the 3FFE B00FFF /56. And we have one link, the serial 2/0, that goes to the RTP campus. Configuration-wise, rather simple. We are looking at first and most important step is enabling the routing process on the routers, IPv6 unicast routing. Obviously, from the terminology, it's obvious that we are talking about unicast processes, not the multicast. And then on the interfaces, we enable IPv6. These interfaces most likely will have IPv4 on them as well, but here we're just showing the IPv6 addresses. There are several ways in which you can do this, but this is one way in which we show clearly how the interface ID is defined. In this case, for example, for fast Ethernet 0/2 on router R1, the prefix is 3FFE B00FFF2. The interface ID is 1, statically configured. We could have let the router choose its own interface ID with UI64. If I'm using some terminology that is not familiar because maybe you didn't work that much with IPv6, please let me know. I'll explain it. Once we set up all the IPv6 addressing, we can ping between the routers. We want obviously to turn on the routing. The choice was ISIS. We're going to have 2 areas, one in IRTP, one in San Jose. Enabling ISIS on the router, we start the ISIS process. We define the IPv6 address family, define the area, and enable ISIS on each interface. Pretty straightforward. RTP side, configured in a similar way. We have a different prefix here. We assign that prefix, we cut it in /64 throughout the routers, and we're going to enable ISIS as well. In between the 2 sites, we choose to have a link that runs ISIS level 2. As you can see, we enable the circuit type on the serial 2/0. Now, someone mentioned earlier NATGP. Basically, we want to have at one point or another in our network, we want to have sort of an interface between the V6 world and the V4 world, right? Because as you can see, V6 and V4 really don't talk to each other in this case. No tunneling, V6 doesn't even use V4 in order to transfer this traffic, but there is no window between the 2 worlds. So NATPT is going to be your window between V6 and V4. And if you have within an island devices that want to talk only within a dual stack island, devices that want to talk only V4 or only V6, then you want to have NATPT enabled. And on this particular router, we have NATPT enabled for such V4 host that is not using IPv6. BGP configuration for the setup. We use eBGP to our service provider and iBGP between the 2 sites. In terms of configuration, again, just briefly going over the BGP configuration, we have the process enabled and we define the 2 ASs for the campus and for the ISP. What I wanted to show is pretty much configuration-wise something that is similar to what you were familiar with in IPv4. The neighbor definition, however, as you can see, is the neighbor defined is your next hop identified with the link local address. I'm assuming that everybody is familiar with the link local addresses, but basically are addresses that are used only for the local link, to exchange information. And why do we use that as the next hop? Well, IPv6 can do some portion of the numbering very easy through router advertisements. Addresses can change between the routers. Global unicast addresses can change between routers on the same link. But the link local addresses typically do not change. So this way, using the link local as your next hop is a very easy way to nail down that neighbor relationship very, for the long run. But you want to make sure that when you're going to advertise or send information about your routes, you are not going to provide the link local as a next hop. Why? Because the router is specifically told to not forward traffic to link local addresses. Okay? So that's why we have that route map down at the bottom that says whenever you're going to advertise your prefixes, make sure that you put your next hop to be your global address, not your link local. And this is the link between customer site ISP. Yeah. Pretty much configuration-wise, everything stays the same. Don't think I need to talk anything about this. And this is the IBGP connection. Same concept. The same way defining of the prefixes, the neighbor relationship is defined the same way under the address family IPv6. The network definition over there is just basically making the router to advertise that prefix, and then the route map down at the bottom again to make sure that the router advertises the prefixes with the right global unicast address as the next hop and not the link local. There is another statement that should be in the BGP configuration that is going to show up in our 6P example, which basically will tell the router to not assume that IPv4 is the only protocol type that is going to be ran. Then, to complete this example, we want to make sure that the traffic that gets to the ISP then goes out to the internet and connects out to other sites on the V6 world. So for that particular segment, we chose to just set up a static tunnel to the inter-exchange. And it's a typical example of manual tunnel. Any questions so far? I'm just curious, how many people run MPLS actually in their network? Okay, so maybe a little bit more interest in 6P. 6P is a migration technology or migration strategy to hop IPv6 over IPv4. And it's actually a very powerful technology because it allows you to do that with minimal impact on your core. That was the goal of 6P. And it leverages all the experience and all the knowledge that we gain with running MPLS, VPNs, and so on and so forth. So if you look at this network where you have MPLS 4 and you have your PE devices, the idea of 6PE is you enable 6PE on the edge devices where you have customers and only there. And then information, IPv6 packets are going to be tagged with a V6 tag, then tagged with a V4 tag to cross the core. The packets are going to be switched based on the V4 tag all the way to the next hop, to the next 6P router. That tag stripped, and then switching done, or the destination of the packet being identified based on the V6 tag. So we're going to go through the packet forwarding information shortly. In terms of how protocols are being distributed across the network, well, you have your V6 island. Over there, you're going to have all your V6 world stuff. You have your V6 addressing, and you're going to have your V6 IGP, or maybe you can use BGP to talk between one of those V6 islands and the 6P router. In the core, you're going to be left with whatever V4 has. So you're going to have your V4 addressing, you're going to have your V4 IGP, you're going to have all the mechanisms that you're using to exchange the tags, be it LDP, RSVP, BGP. And then you have your BGP, multi-protocol BGP sessions between the three routers. So, how exactly 6P works? Well, in this diagram, we have two routers that advertise or that host two prefixes. On the left-hand side, you have 2001-0420, and on the right-hand side, you have 2001-0421. Each one talks via an IGP, a V6 IGP. They talk natively to the 6P router. So 6P1 and 6P2 interfaces facing those routers are enabled only for IPv6. 6P2 via BGP is going to advise 6P1 that, hey, I know about 2001-0421, and if you want to reach it, you just go to the IPv6 map IPv4 address 192.254.10.17, which is his own address. Along with this information, 6P2 is going to send a tag saying, whenever you're going to send packets for that guy for 2001-0421, please also attach this IPv6 tag to the packet, so I know how to deal with it. Okay. Now, when we move back to 6P1, 6P1 will have the following information. I know how to get to 2001-0421. My next hop is going to be the address column FFFF column 192.254.10.17. That is the IPv6 map IPv4 address. So I build an IPv6 address out of that IPv4 address. That will be my next hop. I also know that if I'm going to send this out, I have to attach an IPv6 label, which was advertised by 6P2. And I also know that if I want to get to 192.254.10.17, I have to check my label, my v4 label for that prefix. I learned how to get to that network via IPv4 IGP, and I know the tag that was exchanged via LDP or RSVP or so on. Okay, so now here is, with some animation, pretty much the same discussion. 2001 is advertised, 2001-0421 is advertised via the IGP to 6P2. 6P2 is advertising his own 192.254.10.17 network in the IPv4 world all the way to 6P1. But then via his BGP session is advertising 2001-0421 along with the next hop. Well, it's not just the v4, it's the IPv6 mapped IPv4 and a label. And then, 6P1 can advertise via these v6 IGPs to his clients. So now let's see how the packet travels through this network. Most flash router is going to send an IPv6 packet, plain and simple. It knows via his own IGP that he has to send it to 6P1 in order to reach 2001-0421. 6P1 picks up the packet, looks up in his own routing table, and sees that if he wants to reach 2001-0421, the next hop is going to be column FFF 192.254.10.17, which is IPv6 map IPv4 address. So you need to know, oh, wait a minute, this means that I'll have to encapsulate this packet with a tag, with IPv6 tag, and then with an IPv4 tag to do 6P. So he's going to go and add, besides the NPBGP learn label, the v6 label, which is the yellow one, is also going to add the LDP label for 192.164.10.17. For the packet along, now, the core of the network has no clue what's in that packet. All those routers care about is the top label, which is the LDP exchange one. So the next router is going to see the label, the green label, is for 1017 is going to do the swap, the typical MPLS stuff. So happily swapping labels, the router gets all the way to the code, all the way to P2. P2 is the penultimate hop. So at the penultimate hop, I pop the label. Now, this is the reason why we need an IPv6 tag, in order to make sure that this mechanism works with penultimate hop. If my MPLS network uses penultimate hop popping mechanism, and I don't have the IPv6 label inside, if P2 pops the MPLS label, its P2 gets this IPv6 packet on an IPv4 interface. What do I do with it? Nothing. I just drop it, right? So, with the existence of the IPv6 label, now P2 is going to pop the top label, and it's going to forward the packet to 6P2. The packet still has a label. The packet still has the MPTP exchange label. So he still knows that he still can process it. He still looks at the label instead of looking at an IPv6 packet. Now he gets that label packet, does a lookup on the label, sees what that means. That points him to his V6 sort of to the V6 world. Pops that particular label, the yellow label, the IPv6 label, and then does an IPv6 lookup and forwards the packet wherever it has to be forwarded. Just a point of interest here. What we noticed was, well, when you do 6P, you actually do a lookup on this label, right? On this yellow label, the V6 label. These are rather small entities compared with the actual address. So if you can actually assign one label, a unique label for each prefix that you learn over here, you can actually do a much faster lookup by looking up a very small label and binding it to your outbound interface, and actually do a lookup on the whole IPv6 address. So for example, our original implementation used aggregate labels. We used 16 labels, and we just assigned them round robin frequently. If you assign a unique label to each prefix, lookup is much faster. Saves you a lot of time, a lot of resources. All right, 6P is pretty much everything clear with 6P. Any questions? Nope. Good. So first of all, I'm not sure why we would not want that. Why we would why we don't want to have IPv4 and IPv6 running together. If you have a TE tunnel or just MPLS. Well, so the idea would be, I didn't want for the cloud to have any clue that I'm doing this 6 at the edge, that I'm doing this 6 at the edge. And moreover, it's going to be rather tough to make a differentiation between the paths. Just plain MPLS, because I'm just plain MPLS. Because as you can see, I'm using 4 paths that are being used for traffic. So the tag that I'm going to use for my IPv4 IPv6 traffic is going to be the tag that is going to be used by anybody that and wants to be forwarded to router or his advertising admin. So it's going to be hard to make differentiation. Now, obviously, what we are talking about here is 6PE. But there are other mechanisms that you can deploy using an MPLS core, but not 6PE. You can build your MPLS tunnels, for example. And then you can set up your own path only for your IPv6 traffic. But then that's different. You don't have the dynamic aspect of the deployment that 6PE offers. You're just going to have nailed tunnels. Some information on standardization. I'm going to skip over this. Some of the benefits of 6PE. 6PE is it's pretty good. It works very well. It scales very well. We've seen it in production. It's a very good solution. You're familiar with VPNs, then you understand 6PE. Pretty much the same concept. What you have to keep in mind, though, is that 6PE is sort of provides a global connectivity for everybody in your network. It doesn't differentiate between end users. So 6PE offers you a one big IPv6 cloud on top of your network. Everybody sees everybody. Okay, so it's if you would 6PE, you can make the analogy with V4 VPNs. It's as if you have one big VPN for everybody. Okay. Excuse me? Actually, I'll show the configuration-wise. I'm just drawing an analogy. I'm just drawing a parallel. If you're familiar with VPNs, that's how you should look at 6PE, as being one big VRF. But that handles only V6 traffic. So let's go over the configuration, and that will make things a little bit more clear, maybe, how the configuration is done. But bottom line is, the idea is that it's pretty simple, it's pretty straightforward to implement. Doesn't affect your core, which is a big factor. It's very dynamic, it scales. Forwarding performance is excellent. Forwarding is done in hardware throughout. So, it's going to have little impact on your performance of the network. The only thing that you have to look is some of the hardware resources, but other than that, it's okay. Of the cons, you don't want to do 6PE if you don't run MPLS. Don't turn on MPLS just for 6PE. You need to understand MPLS and BGP, as most of the people do nowadays, and requires an upgrade at the edge. So your 6PE devices, your PE routers that will do 6PE will have to be able to have the feature enabled and talk to it. Yep. You can do LDP, RSVP, and over PE tunnels. That's good. And there is one more comment that I want to make on cons. I think I'm going to talk a little bit about it. No multicast. So, if you look on the long run, multicast is part of your service that you plan to turn on as a service for multicast IPv6. Unfortunately, no multicast over 6P at this time, but work being done on it. Configuration. There are two commands that are relevant. Neighbor, send label. This is under BGP. So you advise the BGP product to send the aggregate labels. And you have a global configuration, which is MPLS IPv6 source interface. It's explained down there. Can make sense. Some of the few show commands that are interesting and worth looking at when you enable troubleshooting. Show BGP IPv6 neighbors in order to see the capabilities. Show BGP IPv6 unicast for a certain prefix. IPv6 route. MPLS forwarding table. This will show you the IPv4 side of things, the IPv4 tags that are going to be used. Show BGP IPv6 unicast label. That's going to show you the inner label used, exchanged by NTBGP. And show IPv6 set. That will show you the two labels together in a stack. Configuration-wise, on our diagram, we had the 6E router, which was left mode, native IPv6. Oh, sorry, go ahead. So, where is that? Okay. So, 6E routers, never mind about it. It's native IPv6. You don't have to worry about it. Talks over standard routing protocols with the 6P router. The 6P router is where most of the action is. We have MPLS IPv6 post interface loopback 0, the first command that we mentioned. And then the BGP configuration is relatively simple. You just have to turn one command that was I mentioned earlier that was not in the example for BGP for native for dual stack. One command that you should keep in mind is no BGP default IPv4 unicast. Has to be there on BGP in order for the router to think that it's not v4 only, it's going to do v6 as well. Address family IPv6, over there you're going to have the neighbor. As you can see, it's a v4 next hop, right, for 6P. We are looking at the within the v4 world. So it's going to be the next hop v4 address, and you advise it to send a label. Some of the commands, I'm going to go really fast through some of the show commands. Show BGP IPv6 neighbor. What you want to see there is you want to see that the address family IPv6 unicast is negotiated, and you want to see that the capability is received, advertised, and received later. I was talking about that IPv6 mapped IPv4 address. As you saw in my configuration, the next hop was 10.10.20.1, right? Well, via MPBGP, I'm going to advertise the v6 prefixes behind me. Next hop is this IPv6 IPv4 mapped address, which is colon FFF 10.10.21. So I build an IPv6 address out of my own v4 address. So the router over there is going to build a BGP neighbor with me at 10.10.21. In his routing table, the next hop for the IPv6 prefixes behind me will be colon FFF 10.10.21. Is that clear? Show IPv6 route. We see the IPv6 route being advertised via BGP, and we see the next hop to be that IPv6 mapped IPv4 address. Show MPLS forwarding table. Here we have the tags, the prefixes that are the IPv6 prefixes listed, and they're listed with aggregate. Untagged one is a network that is directly connected to the router. Show BGP IPv6 unicast label. Here you're gonna see all the labels that I learned along with the prefix. So I build a neighbor relationship via BGP with 10.10.21 over the v4 world. That guy sent me the following information. He said that he knows about 2003 column 1, column 1, column 30, column /64. If I want to get over there, my next hop is going to be column FFF column 10.10.21. And the label that I should use, the v6 label that I should use when I send a packet via 6P is going to be 124. Okay? Now, okay, there is a little bit of a small piece missing that would make everything just pretty. Okay, if I do a show IPv6 set, as I said, I'm able to see the stack of labels. So as you can see, I can see that my prefix 2003.11.30.64. Next hop is again that IPv6 IPv4 mapped address, and I look here at the labels. 124 is the inner label, which is the v6 label that will be cleared by MPBGP. Can anybody tell me what 129 is? The top source for what? exactly. For router that advertises. In other words, 129 is the LDP, RSVP exchange label for 10.10.21. Right? So this label 129, I got it via LDP, and I will use it to get the 10.10.21, which in turn will look at 124 label and we will know what to do with it. We'll know it for IPv6. We will know to do the lookup for IPv6. Deploying, when you plan to deploy 6P, what you do is you want to start at the edge and then maybe add a few routers. If you don't want to mess with your production routers, add a small router over there at the edge, make it a PE router, turn on 6P, and sort of, if you want, isolate a little bit that way resources. But then, as your customers grow and grow and grow, and they grow so fast, it's amazing, just move towards the core. Enable the major routers for 6P, move towards the core. And then turn on services. Once you have 6P, you have the unicast connectivity, turn on services like multicast, not so much, right? Not over 6P. I'll talk about an alternative. But you can turn on TOS for 6P. You can turn on VPNs for 6P. So here is an example. You have your own network where you have V4 devices doing their own PE, their own exchange of information. Maybe you want to turn like a small router there at the edge. The V6 port is really small, the green portion over there. And you have the 6P routers talk to some route reflectors. You want to use route reflectors exactly like you do with VPNs for scalability purposes. It works with 6P like flex VPN. And you have small patches of V6 here and there, green patches. Two routers in some of the edge areas and maybe one in your data center to provide services. And then as your number of customers grows, then you start to move your devices, you increase the size of your IPv6 island, and you move your devices closer to the core. And you turn 6P services on the main PE routers that you're on. Same scalability information. There's a small slide here on inter-AS, which is, you use 3 labels here. I'm not going to go into this because I'm really out of time. But I can definitely talk about it if you want inter-AS or carrier, supporting carrier. Just a quick note on load balancing. It works just for reference purposes. You look at load balancing in 2 areas. At the 6P router, it's done based on hashing source destination, and on the P router, now is supported on source destination hash as well. Works. Things are even better. Now IPv6 multicast. Like I said, there is no way to do it over 6P, and it's the old problem with MPLS, altogether. We all know that MPLS does not really support multicast, so there are all kind of workarounds. Same thing with 6P. Work is being done to do it, to support it in the future, but for now, you might want to consider an overlay. If your customer really wants to do multicast, then you might consider an overlay with some that also leverage MPLS, like UMPLS tunnels, for example, can be used for multicast traffic. QoS is on the roadmap, not supported at this time. VPNs, on the other hand, are supported. We call this feature 6VPE. We have it on our routers, and same concept. It's pretty much going to divide this big IPv6 cloud that 6P put together. It's going to divide it into smaller clouds that are private and are used for customers. So now here is the interesting thing. Why in the first place we really need VPNs now, right? I mean, V6 is the next thing, right? We have all the addresses in the world. We don't need private addressing. We don't need to hide our addressing schemes from others, except for security purposes, which is a big fact. But so why do we need VPNs? Well, we need for the fact that we are used with VPNs. Network administrators are used to running VPNs, and we still have the security problem, and we still want to keep things within our network and for other people not to see them. But the question then is, how do you get out of these VPNs, right? I mean, how do you get from these IPv6 VPNs and connect to somebody else, to another network, to the V6 internet? ISPs came to us and said we really want VPNs. I said, okay, well, if you really want them, sure, we can do them. But then the question now is, you have your VPN, you have your own world, how you get out of there? So we have VPNs, now we have to work on the next step, trying to get out of them. That is not being done yet. Does that make sense or not? So just food for thought. One thing that you could do is with V6, since we support so many addresses on the same interfaces, what you might want to do with the VPN deployment of V6, you might want to have two address schemes on your network. One address scheme that goes out to the internet, so goes on over a leaky VPN out to the internet. And one addressing scheme that you use inside your VPN or inside your enterprise, inside your domain. And then you let SAS to do the job for you, and hopefully does the right job of selecting the right source address whenever you send the traffic. I pretty much talked about this slide. As you can see, 6P has traffic for all clouds, yellow and green. 6VP instead builds similar to same way as in IPv6 and IPv4. Different routing tables, different folding tables, and so on and so forth. Configuration-wise, if you did VPN on our routers, 6VP is exactly the same thing. As a matter of fact, it was just a change in the VPN code to support the V6. Well, I'm out of time, so I'm not sure. Shall we go? Okay. One of the things that we noticed was service providers were interested in using IPv6 for broadband access. Why? Well, because broadband access offers you the opportunity to get more money out of your customers, right? You can offer them more services, like video channels, audio channels, and so on and so forth. As an example, in Japan, cable TV is not such a popular thing. So why not use some of the broadband channels to actually deliver paid TV channels, Speckle, Disney, or things like that, right? So broadband, deploying IPv6 in the broadband environment got a lot of interest. So that's why we decided to actually cover this example of, discuss a little bit about broadband access. So in principle, IPv6 should really not be concerned about the layer 2 stuff, right? Whether it's DSL, whether it's fiber to the home, cable, and so on and so forth. Well, things are almost true. For most of these access media types, that's the case. Just put IPv6 on it, regardless of the media. Things are a little bit different in cable. DOCSIS, the current version of DOCSIS that is being used, is not really conducive to IPv6. Does not have all the elements necessary for the cable pieces to support IPv6. So, if you're thinking about doing IPv6 over cable right now, your not best bet, your only bet is tunneling. Everything else goes all the way. You can do dual stack native with all the other media. And actually, Salman and a colleague of ours and myself, we wrote a draft about broadband access. If you're interested in more information on the cable side and the problems that we face there and the work that needs to be done there, we encourage you to go over it, or we can answer some of the questions. ADSL and FTTH access. So whenever you're going to have one of these media, we chose ADSL and FTTH as an example, you have several ways in which your customers can gain IPv6 connectivity. they can just have layer 3 connectivity, dual stack, enable IPv6 natively between the customer as a PC or as a customer premise router and your access router, the one that you manage as a service provider. Or what you can do is you can use some form of PPP connection. So here it's just a discussion on how these protocols stack up. We show two models. One model is plain PPP, so you just take your IPv6 packet, send it over PPP, and in between the two routers do not necessarily have to have IPv6 natively enabled. That would be sort of like a point-to-point model. And then we have an aggregation model, which is the second one, where actually what you do is, see, in the first case, the PPP session is terminated with NAS, take it out of PPP, the packet is taken out of PPP, and then it goes into the IPv6 cloud. Second example, you might want to do aggregation, so you might want to aggregate some of this PPP session all the way to an aggregating router, to an LNS. So you take all the PPP sessions, bundle them up into L2PP, take them over an L2PP tunnel to the LNS, well, you unwrap the whole thing and take the traffic into the IPv6 world. And here is just protocol stack in a little bit more detail for these DSL access. Configuration-wise, in this case, what we are looking at is obviously the interface portion, the APM portion, but then we're looking at the PPP session. Configuration is on the dialer, and besides the PPP connectivity, we put one statement that is relevant there, which is the IPv6 address auto configuration, which advises the router how to get its address from the NAS. And also we have to have the static route that says the typical default route that says all your traffic, send them out over dialer 1. And then the termination side on the NAS. We support all the extensions that refer to IPv6 in Radius. They are all listed here for your reference. I'm going to skip real quick over this. Addressing allocation. Obviously, when you're going to start to build this business case for your broadband access, IPv6 broadband access, you want to think about addressing. Now, there is plenty of addressing out there, but you still want to make money out of it, maybe, like someone was mentioning. The policies nowadays are, you're as a service provider, you take your slash 32. You might want to assign your customer slash 48 if they have a small site over there, or slash 64. Preferably, you don't cheat the customer and don't go higher than 64, so you don't go like 70 something or so on and so forth. But you as a service provider might choose to take some of the bits and ask the customer for money if he wants to get all 48, so on and so forth. But policies, the recommendations would be go slash 48 or slash 64. The one thing also to keep in mind, this slide pretty much stays what I just said, but one thing to keep in mind is with V6 we sort of try to stick to our promise that we will give customers an address to keep for the long run. Not like with V4 where we were so stingy and we say, all right, here's an address, you use it for 2 hours or 3 hours, then I'm going to take it back and I'm going to reuse it. So that in itself might help in some situations. It might help with the management of the addressing, and might help the customer with his configuration of the site, simplify it. But it might introduce some small complications in how you do things in your own network as a service provider, especially when you do aggregation. To give you an example, if you have, in one of our discussions, if you have two terminating points for your tunnels, whether they are PPPoE or they are your L2PP tunnels, And you have your customers that they can connect to any of these LNSs or NASs, right? If I'm always going to give my customer the same prefix, and he can end up in any of these routers, then I'm starting to put holes in the prefixes that each router can advertise. So now I'm going to have mixes of /64s here instead of being able to summarize them to /48s, for example. So policies or some thought has to be put in this process. We have a small discussion also on the draft in this. You might want to put some policies in terms of how customers can connect to different locations if these customers will always keep the same address. But like in V4, you might also choose to give your customers temporary addresses. In this first example here, this is an example where my customer is always going to get the prefix 3FFEC00, and is going to always get that particular ID if it's just a PC, 0001. But then the next two examples give you some situations where you might want to give short-lived addresses, /128 from a pool or /64s from a pool. But one of the really cool things that we have in IPv6 and we want to talk about is another means to actually provide customers with prefixes and let them dynamically manage those prefixes and distribute them within their network. And that particular mechanism is called DHCP v6PD. I'm not sure how many in the room are familiar with it. But the idea would be that me as a customer, whether I'm at home and I have a really small network, or I'm a small enterprise, home office, I can actually go to my provider and dynamically ask for a prefix for my /48 that I'm supposedly entitled to. And then once I'm getting that /48, I'm going to in turn go ahead and distribute it, cut it up, and distribute it to my internal users or my internal interfaces. So let's see how this works. Let's say that I have my here's my ISP PE router, and I have my CPE router, which is the router that is on the obviously customer premises router. And protocol-wise, on the customer side, I'm using neighbor discovery, I'm using my DHCP, all the good things that IPv6 uses for the users, for the users to exchange any information that they need to. Get their own address, get DHCP information, get DNS information, so on and so forth. The CPE, in turn, talks about whatever link was established between it and PE router, talks DHCP, and then the PE router uses AAA to authenticate, alright, and so on, get the information that it needs for his customer from the radius. Now, first of all, there is one step that was missed here, in that CPE comes up, actually let's do it. The CPE router comes up, establishes the link between it and the PE router, and basically sends a packet, request, saying, "Hey, I'm looking for a router that can give me a prefix, can give me a network address." The PE router receives that packet and authenticates, talks to the radius server, authenticates this customer, and gets from the radius the information that it needs, whatever prefix it can give to that customer. Then the CPE router, the PE router tells the CPE router, "Hey, I'm a DHCP-PD router. I can give you a prefix." The CPE router comes back and says, "Okay, fine. How about you give me a prefix?" And he sends a solicit saying that he's looking for prefix delegation. The PE router, based on the information that it got from the radius server, is going to send a DHCP reply saying, "Okay, here is your prefix that you can use, a /48, for example." The 6P router, the CP router takes that prefix, that /48, and then it cuts it in pieces, however it decides to, and assigns those pieces to its own interfaces. So each of its interfaces will now get a slice of that /48 or whatever it was that he received from the ISP. Once it assigned one of those pieces to the interface that connects to this host, it's going to start sending router it starts to send out router advertisements saying, here's the prefix that you can use. The host can auto-configure itself using the regular IPv6 auto-configuration, and then it can continue with the process of getting itself capable of talking on the v6 world by sending a request for DNS services and so on and so forth. Configuration-wise, real quick, I enabled the router to be a DHCP client over there on my dialer interface. So it's going to be a client towards the NAS. The NAS is going to receive that. It's going to be able to provide him with a prefix. And any prefix that this router will get via the dialer one, any prefix that he's going to get, he's going to call it DH-prefix. Then in turn, once he got that prefix, he's going to go to his own interface past Ethernet 0, and he's going to say, my address is the prefix that I got, the DH that prefix, plus those extra bits up to /64, plus my interface ID, which in this case I decided to be an EUI 64 build address. Any questions on that, so DHCP-PD? Here is some information on the draft that we mentioned. We encourage you. And that will be pretty much it. DHCP works great. It's implemented. Actually, it's in fact it's using in production. It's being used in production. DHCP PD. Yeah. It's very practical. Especially for customers, especially if they have like a small site with a small router. Well, one of the customers that we were working with, for example, they plan for each one of these sort of home networks or like small business networks. They just give them a /48, and then the customer slashes that in /64s and assigns /64 to each interface. Because you don't want on the client side, you don't want to go beyond less than 64, because you still want to keep the UI, so. Thank you.